It is an honor to introduce Professor Jim Dunlop from the University of Edinburgh as our speaker today. He's been described as, and I quote, the most successful multi-wavelength UK astronomer of his generation. Indeed, throughout Jim's career, he's made foundational contributions to the field of galaxy formation in an exceptionally broad and deep fashion. He's pioneered the study of radio and submillimeter galaxies, the evolution of the stellar, star formation, dust, and black hole content of the universe over basically all of cosmic time, and hunted for the very most distant galaxies at the highest redshifts. He's been at the forefront of using facilities such as SCUBA on the JCMT, HST, ALMA, and most recently, JWST. Jim is also notable for his leadership. In addition to sustaining an incredibly active research group of students and postdocs, he has led the Institute for Astronomy at the University of Edinburgh twice and spent several years recently as the head of the School of Physics there. Jim has been honored with many awards throughout his career, including the Darwin Lectureship and Herschel Medal of the Royal Astronomical Society, a Royal Society Research Professorship and Wolfson Research Merit Award, and is an elected fellow of both the Royal Society of Edinburgh and the Royal Society. Currently, he leads one of the largest JWST surveys of the distant universe called PRIMER, which is what he's going to tell us about today. So welcome, Jim. Thank you. All right. All right. Let's get you done. Okay, that'll work.
Everyone hear me? What Alice didn't say is that first description was, we laugh about this because there were so many adjectives before it. The finest generation from somewhere who works on this data, that it became a running joke as to how, to what extent Richard Ellis was actually praising me. But anyway. Right, if you've enough adjectives, it's bound to be true, right? Anyway, it's lovely to be here. I haven't been in UCLA itself, although I've been in LA and Caltech on many occasions. Thank you for coming. I might fall asleep during the talk because I woke at 3 a.m. and I've had, well, when I showed it to Ross McClure what my schedule was that Alice had set up today, and he said it seems more like a Japanese game than a visit to UCLA. So this is the 12th meeting of the day or something like this. Anyway, see what happens. I said I would talk about early galaxy formation with JWST and ALMA, and then I decided it's actually too much. I'll say very little about ALMA, but I'd rather tell you more of a coherent story about JWST. My understanding it's a broad audience, so I'm going to get about 15 minutes of why, what, and the basics. Then move on to this primer survey and explaining what we can learn about early galaxy populations statistically. So this is UV luminosity function of galaxies. And then a simple model to interpret it with various predictions that we can make. And then I'll make some comments about recent papers that suggest some crazy results. And this is maybe why the talk shouldn't be recorded, but we'll see when we get to that point. And now this doesn't work. Great, okay. Nothing works.
Maybe you need to say okay to the recording.
I've done that.
Right now it should maybe work.
I'll try stop sharing and sharing again. There you all are. Hold on a second. Best laid plans. Something about Zoom sometimes can do this. Let's say, okay, that's back. Okay.
What's happening?
I'm trying to reshare. So on my computer now, the PowerPoint seems to be working. So I just need to reshare again. Okay, this is working, but I'm going to stand well away from the.
You need to move.
I have. Let me double check. See if that.
Jen is muted, right?
Just turn the sound off.
Turn the sound off.
Okay, now try. No, it's okay.
Is it better?
Yeah, it's better. It's fine. Okay, great. Okay.
Hurrah, okay. Okay, why do we do this stuff, which is difficult, looking at small faint smudges at the edge of the universe? Here's some key science questions. You might be interested in cosmic dawn, when the first structures actually lit up, when fusion started. Then there's a kind of obsession about cosmic hydrogen reionization, which I sometimes join in on and sometimes don't. But it's a phase change in the universe, and one way to look at the early universe is think about how the hydrogen got reionized and couple that to galaxy evolution. Even if you don't care about reionization, you might care about how early galaxies form, what limits the drives early star formation, various people in the room work and feedback, simulations or observations, the whole issue of when cosmic dust formed and how that affects our view of the universe. In extremis, and every time we get a new facility this comes up, do you find things that are old enough to be contained in the universe? Do you find early galaxies that are hard to make in lambda CDM? And down at the bottom, maybe the easiest thing to understand from a human point of view, if you're trying to explain to the person in the street why you're doing this, you might be interested in where the elements of life came from, all the elements that are not made in the Big Bang. Standard thing you'll give in all your public talks. That's the science version. Here's the one for the person in the street. I'd like to know where the carbon comes from. I'd like to know where the oxygen comes from. And I personally would like it to be deeper into my lungs, but that's a different story. The iron and all the stuff that grows intelligence in the human race up to the point of making a beer, shown here on a table in Scotland after I've climbed a mountain. So that's a simple origin story explanation of what we're doing. The key facilities, most people will know this. There's probably 6 telescopes on here that have been combined to do a lot of the recent work. Hubble, obviously, the VLT and ESO, and VISTA, which is the wide field survey telescope that we did the Alta Vista survey with. All of the wide field ground-based stuff benefits from optical data from Subaru, and then more spectroscopically from Keck. A lot of the redshift work before JWST came from Keck. These 2 pictures remind you how great it always is on top of Mauna Kea, if you can get there. And of course, ALMA, which is going up recently. So even today, when I talk about JWST data, it's always coupled with Hubble data or with VISTA data. You need the full optical infrared to do this work, even if JWST is the headline facility. A few slides about where we were pre-JWST. It's not that long ago. I mean, it now seems like a world ago, but it's not that long ago. Here's my Mickey Mouse slide to insult people in the room. Redshift. I just think there might be some non-astronomers here, so this is hopefully fine. Redshift is a stretch. It should be called red stretch, not shift, because it's simply that the light traversing the universe, as the universe expands, the light itself is not a source of the electromagnetic field, unlike gluons, etc. So there's nothing to stop the light wavelength expanding. And so lambda observed over lambda emitted, which we call 1 plus Z, so that we don't have a 0. It's 1 or it's 0 when the 2 things are the same. is an indication of the size of the universe now, of the size of the universe then, and then your cosmological calculation turns redshift into a measure of look-back time. And until JWST, when we were doing this with Hubble, and I made the point here that Euclid, which was launched last summer, has a similar redshift limit because you can only get to about 1.6 microns for a different reason. Hubble's a warm telescope, so it doesn't work well beyond 1.6 microns. The way we do redshifts, if we don't have spectroscopy, is we have a continuum here of a galaxy, and it will redshift through all these filters. This is Hubble blue, Hubble green, on into Hubble's infrared things after it got its wide field camera. And this is as basic as it seems. The galaxy will drop out. Sometimes they used to be called dropout galaxies in different filters due to the absorption by hydrogen. Okay, this is when Zoom will slow down all videos. Sticky, redshift 4, redshift 5. Initially, it's the Lyman limit, then it's the Lyman break at 1216. By the time you get to the last filters with Hubble, you can't really do anything seriously beyond redshift 10 because you would like a couple of detections above the Lyman break to make sure the object's still real. Okay, and a lot of the problems in this field, and you might think this is an old-fashioned idea, but there's a whole bunch of papers recently still doing this dropout technique and doing it very badly. And I'll explain why. And with that kind of work from the ground and from Hubble, this is what the galaxy luminosity function looked like before JWST. This is a plot from an ex-student of mine, Rebecca Bowler, who did a lot of good work with Ultra Vista. The luminosity function is just the co-moving number density per unit luminosity or per magnitude, because we are silly astronomers. This is UV luminosity or UV magnitude, so it goes backwards. Bright galaxies, faint galaxies, different redshifts, 4, 5, 6, 7, 8, and 9, which is the best you could do before JWST. And you see a couple of interesting things. Galaxies become less numerous as you look back to higher redshifts, and this will become important later. It was already clear, but you can see how dodgy the redshift 9 stuff is, big error bars. But it was already clear that there was a hint that bright galaxies weren't fading away very much with look back time, whereas your typical galaxy near the break in the luminosity function was. So galaxies were getting rarer as you look back to early times, but the shape of the galaxy luminosity function, the demographics of the galaxies was somehow some hint it was beginning to change. And in fact, it depended who you spoke to, what people thought would be the number of bright galaxies you would see at higher redshifts with JWST, because it depended how much you believed that this was holding up and bright galaxies were somehow not fading away as much. So we knew this much. We knew sensible evolution of galaxies becoming more rare, and there was some hint of this evolution in shape. Meanwhile, I apologize for the spectroscopists in the room. This is a very short summary. People were working really hard with ground-based facilities to get spectroscopic redshifts where you really knew what was going on. You identify your emission line, you think you know the rest frame of the emission line. And so the photometric surveys with the colors looking at this Lyman break effect, they're getting you to kind of redshift 9, 10-ish, and actually so were the spectroscopic surveys. So at the time, just before JWST, this Nature Astronomy paper reported this carbon-3 doublet in an object now famous, GNZ11, which actually Pascal Oesch had selected based on photometry back in 2016. And so this was the record redshift, 10.957. Seemed quite good because the photometric redshift was about 11. And meanwhile, with ALMA had started doing something it wasn't really designed to do. ALMA was built as a sub-millimeter machine to do molecules, CO, dust, etc. Turns out to be a brilliant atomic or ionic spectrograph for high redshift astronomy. And there was already an ALMA record as far back as 2018 for a redshift at 9.1. Again, didn't seem too far from the photometric redshift. What's going on here, this is the oxygen 3 that we're so used to seeing in the in the optical regime, oxygen 35007 line, which is here, this forbidden transition. But down here, there are other smaller energy, longer wavelength transitions. There's an 88 micron line and there's a 52 micron line. And there's, no, it's 3p, so they're not changing angular momentum, but these are the J quantum numbers. So these are spin changing transitions that are there for semi-forbidden, or fully forbidden rather, magnetic dipole transitions. This 88 micron line is what's seen here, shifted further into the proper millimeter, sub-millimeter. And so weirdly, some of the redshift records for a while seem to be coming from ALMA. And this will come back again because there's a very recent paper again exploiting the O3 transitions right down at the low energy levels. Problem with that is that redshift is absolute nonsense. Okay, it's actually redshift 10.603. Apologies to the Keck addicts in the room. This is an example of how, if you're looking for something hard enough, you can see it. That is not the carbon-3 doublet, it's just noise. Sorry, am I making a weird echo here? Okay. So in some ways, this is the end of ground-based spectroscopic redshift records. Okay, JWST era. Did my best to put these to scale. JWST is about 3 times bigger than Hubble. It's a lot bigger than the 85 centimeter tin can that is the Spitzer telescope. And that's maybe the relevant factor, because in the proper near to mid infrared at 4 microns, going from Spitzer to JWST, the mirror collecting area increases by about a factor of over 50. And in some ways, this is why it's been such a revolution, right? The comparison with Hubble is not quite the main thing. It's really the comparison with Spitzer. JWST's got various instruments. I'll just show you the focal plane to make the point that mainly I'll be talking about data from NIRCam. But a lot of the primer survey also is covered by MIRI, which, because it looks at a different bit of the sky, you've got to design a survey strategy that drags MIRI across the bits of the sky you've already looked at with NIRCam. And of course, at various points, I'll show you some spectra from NIRSpec, which is these days being used to follow up all the things we've found with NIRCam and MIRI imaging. So why is JWST good for this photometric redshift selection? This is the same idea. You've got a continuum. By the time you get to high redshift, so this is redshift 7, it's actually really, really easy to find high redshift galaxies because the NuSCO universe is creating such a strong Lyman break at rest frame 1216 angstrom that, you know, it's a factor of 10. There's nothing it can really be confused with. The Balmer break typically can't be much stronger than a factor of 2. So if you've good enough data, easiest thing in astronomy is to find high redshift galaxies. You look for things which hold up in all these other filters and then disappear. And this is just to make the point, unlike with Hubble, by the time you get to redshift 10, in the primer survey where we had 8 filters from NIRCam, you've still got 1, 2, 3, 4, 5, 6, 7 data points above the break here. So this is a completely different world, just thinking, oh, I can see it in 2 filters, but not in the rest. And you can be able to fit the slope. And in principle, without the spectroscopy, with redshift 10, for example, here, you can actually tell the difference between an old population of a few hundred mega years and a very young population. So although spectroscopy is great, the imaging and the photometry that comes from it is very powerful when you can see all the way out to 5 microns, as you can with NIRCam. Just a couple of words about where NIRSpec is now. So NIRSpec's been amazing. I must confess I was surprised that NIRSpec works as well as it does. And I thought JWST is so complicated that even if it's just a nice big imaging machine, that'll be fine. No. I mean, anyone who goes back to Keck to do high redshift spectroscopy after they've seen these is in for a rough ride. Here's 2 galaxies at redshift 12-ish, 12.3. This one's at 12.48. Interesting things, there's tons of carbon, plenty of oxygen, lots of nitrogen. These are in no sense population 3 galaxies at all, and we're already jumped out to redshift 12. This is the most distant known galaxy at the moment. It's interesting how difficult it's going to get with JWST very soon. This object is definitely at redshift 14-ish. That's definitely a Lyman break. You can see it in the two-dimensional spectrum there. It's a slightly sloping Lyman break, and we'll come back to that a little bit. There's actually no unambiguous emission lines in that spectrum at all. So it's a kind of weird thing where you've got a spectrum that tells you that your redshift is right, but doesn't give you a really, really precise redshift because you don't have any emission lines. A few weeks ago, ALMA, O3 again, 88 microns. You might not like that emission line very much in that spectrum, but the ALMA detection's there in the black contours. That was a bulletproof 88 micron detection of the line. And the redshift is this plus or minus 0.0007 or something like this. So this is the right redshift. That redshift is slightly wrong. I mean, it's kind of fine. And it turns out we may end up for a lot of these objects having to use ALMA to get the precise spectroscopic redshift. Lyman alpha in most of these objects is long gone. It's been killed by the neutral hydrogen. If you dig hard enough, you can maybe find a carbon line now that you know from this exactly where to look in that spectrum, but it's very difficult. But it's amazing, right? I mean, we've gone from redshift 10 to redshift 14. We're now less than, just a little bit less than 300 mega years after the Big Bang, and we're getting spectra of galaxies like this. So hopefully ALMA will keep giving out time, because this is one of the big areas that could make a huge impact in the coming year. From my point of view, this is massively reassuring, because with the very few exceptions, this is spectroscopic redshift with NIRSpec against photometric redshift with NIRCam. And in general, despite some of the scaremongering you hear, it's fine. There's a slight tendency for the photometric redshifts to be on the slightly high side, but this is because of neutral hydrogen kind of eating into the Balmer break a little bit if you don't have good image quality or deep photometry. So
based on the templates, isn't it based on the templates or the model for the IgM absorption?
Once you get to very high redshift, there's this idea that things are so neutral that the damping wing, there's a strange terminology for those people who don't do this stuff. So when the hydrogen makes an absorption line, you normally think it would be broadened by Gaussian velocity, whether it's a thing of gas or a galaxy. But the actual absorption line for Lyman alpha is a resonance absorption line as a Lorentzian profile, which is the same thing you get from a damped harmonic oscillator. So these really deep absorptions, what happens is the wing, it's completely optically thick in the middle. The wings, the quantum mechanical wings from the Lorentzian profile spill out because the absorption's so deep, much deeper than you know it is, because it's down below zero. And that if you've got neutral hydrogen just in front of the galaxy, as at very high redshift you're likely to have, that wing eats into the starlight from the galaxy, and so you don't get quite such a steep Lyman break. And if you're relying on the Lyman break for the redshift, which is what you're doing with photometry, you tend to think it's slightly higher redshift because it's been eaten into by the damped Lyman absorber. But the errors are like what I just showed. Is it 14.3 or is it 14.15? Still a good start if you're going to do lots of redshifts without doing spectroscopy for them all. So you might say, why care about JWST imaging if you can do these things with NIRSpec? The things I showed you there are the brightest known things at these redshifts. Right? We will never do the faint end of the galaxy luminosity function with NIRSpec. It's already too hard. And so we'll get example templates of objects, we'll get interesting things. But if you want to do statistical studies of the evolving galaxy population, you have to do imaging just because of the signal to noise you've got. There's some people in this room. Tommaso was involved, still is involved in GLASS, which is now at paper 5 million or something like that. So there was some early, one of the exciting things about JWST is right from the start, there was a few small area imaging that immediately gave some really high redshift galaxies. We now know there's an overdensity in this cluster field at redshift 10 that yielded some early redshift 10 galaxies. A couple of things about this. These early surveys obviously covered quite small areas. A lot of them were single NIRCam pointings, kind of 6 arc minutes squared. Sears covered a little bit more. And in some of the surveys, they didn't have all the photometric bands to get a good quality redshift, but nevertheless, it was a bit of a revelation. So what I'm going to talk about now is a much bigger survey, which we were pleased was approved for cycle 1, but took most of cycle 1 and cycle 2 to complete, which is primer survey. I never know if this translates to the US. Some people say it doesn't. Primer in the UK is a can of paint you buy to put in the wall before you put the proper paint on. Okay. Now I thought this is a good acronym, I promise. I also thought this was brilliant because the whole idea is that this is going to be the primer for JWST programs for years to come, and you'll be able to do more imaging and more spectroscopy. And anyway, somebody at JWST bought this. And this was partly because people were initially worried before JWST was launched. It might only last 5 years. That was the requirement. 10 years was the goal. Now might be 20 years because so little of the fuel was used to stop it at L2. But there was a general panic that if you didn't go straight in with a big imaging survey in cycle 1, you might not have many years to do spectroscopic follow-up. So this was the rationale that we sold successfully to the TAC, because normally you wait a few years before you do a big survey. That's what happened with Hubble. They waited many years before doing a deep field or the Candles project. So this was going right from the start. And I'm not going to say much about ALMA, but I just want to make the point about a survey like this, which has got both NIRCam and MIRI. This is an image of an ALMA galaxy about redshift 4. There it isn't in Hubble blue. There it isn't in Hubble green. There it isn't in Hubble I. There it actually isn't in JWST 1 micron. It's not in Alta Vista Y. Maybe something from the ground in K-band. And then the long wavelength NIRCam filters, there it is, there it is, there it is. Uman and MIRI. Okay. So, well, this is a little bit of an aside because this is not an extreme redshift galaxy, but the whole point is you've completely removed your bias to kind of UV visible star forming galaxies, even at cosmic noon here. And in this, I can talk later to people who want to know about this. This paper's on the archive. Frey Liu, who's the first author as a PhD student, is the cheeriest PhD student I have ever had, as you can see from that picture. And without going into details, this is the sort of thing you can do with JWST. So in the Cosmos primer field, there's about 70,000 galaxies here plotted with stellar mass, because you've got good mass measurements, because you've got red bands from primer. Against photometric redshift, because you've got really good redshifts, photometric redshifts. And it turns out there hasn't been an ALMA survey of a field this size, but people have just been banging into the Cosmos primer field loads and loads of pointed ALMA observations for. Some of them I know why it is, some of them have no idea. But there's 128 ALMA sources just randomly lying in this field. And all of them, bar, that's probably a mistake, all bar 2, so 126 of 128 are above a stellar mass threshold of 10 to the 10. Solar masses are all redshifts. Okay, so that this gets turned into a study about dust obscured star formation. But the point about this is when we did this sort of work in the Hubble ultra deep field, the area was so small, there was no galaxy over 10 to the 10 solar masses beyond redshift 3 in the Hubble deep field. That's because it's 5 square arc minutes. This is 150 square arc minutes. So for the first time, we can just see, and you see the other really interesting thing that we kind of knew from Scuba and Scuba 2. Most of the high mass galaxies in the high redshift universe are sub-millimeter galaxies. You start to light up, but by the end, it's almost not, why would you be high mass? You're either going to be quenched or you're going to be hugely star forming and you're high mass, high metallicity, lots of dust.
Is ALMA all the same wavelength dust continuum, or is it different?
It's all dust continuum. The A3 Cosmos database is a nightmare. Frey's great work was to convert this all to kind of 1 millimeter flux density using the spectral information, try and sort out what are multiple detections of the same sources. Technical details are a bit of a bore, but you can see the cosmic noon, tons of dusty galaxies. And the point here is that this physical threshold of 10 to the 10 solar masses seems to be unbelievably clean and redshift independent. It's almost like once you clear this threshold of about 10 to the 10 solar masses, you're metal rich enough, and if you're still forming stars and haven't quenched, you'll be detected by ALMA. And remember, a lot of these other things haven't been looked at by ALMA. So ALMA's only imaged 15% of the field. So we're putting in a proposal tomorrow, the ALMA deadline, to do the other high mass galaxies in this sample above 3 to the end. Just bang, 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 bang. We think you're going to be a high mass galaxy. We'll just check, are you a submillimeter emitter or not? So that's a diversion. I'm not going to really come back to that, but it just shows the power of what you can do when you've got this level of red imaging. And it's just astonishing how bright these things are in Miri. Remember that Miri is 10 times less sensitive than NIRCam. Shows how red the object is. It's still booming in Miri. Right, back to this is a 3D fly through that in music, but the music will just probably kill us. So we won't have the music.
Can you hear us? Because we can't hear you.
I could hear you, Brad. I think it's their audio.
Here, let's, here. Sorry about this. Okay, just put it
I
down.
think it has run out of battery because of the light.
Yes, this is fine. This is easy to put in. Okay, okay.
Well, okay. And this was quite cool because NGD went and took another same data again. And there the object is in the F150W filter. So in other words, we put in the prior said, I think it's likely to be at low redshift, and in came the other data. If it's in the F150W filter, it's certainly not sitting at redshift 15 because it should have been gone at 1.5 microns. And this is all very exciting. So we did this, and this allows you to push the data. Some people don't like this, but this is what we did. We pushed the data really hard. So with some galaxies that were maybe 70% at high redshift and 30% at low redshift, we split these galaxies and put them in a probability way into the plane. So you might often have a galaxy like this, and you want to know what its probability is between being redshift 9.5 and 10.5, and you literally cut out that chunk of the normalized probability distribution, and you also put it into low redshift or whatever it is, and you just slice up the objects. With the referee who hated this, he wanted to see a precise redshift for all 3,000 galaxies. We don't have it. And by pushing this way, at least you're statistically robust.
So
I-
this type of estimates that you described, are they taking into account also that we have more galaxies at lower?
Yes, that's what I mean by a luminosity function weighted. Right, so imagine you've got no real information for the atometry of the redshift. It will tend to go down to low redshift because you might think this is a circular argument. Well, you're trying to calculate the luminosity function things, but we know the luminosity functions at redshift 2 and 3. And even with any uncertainty, you know roughly what the dynamic range is between redshift 3 and its chance of being at redshift 10. So yep. Yeah.
Yeah, well, this comes back to the idea of a photometric redshift. I mean, you're usually talking about a redshift from colors. So that's ratios. But if you just have photometry at one wavelength, you can still estimate how far the object is because you have some idea of the luminosity function.
That's true, but we're a priori better than that. We've got 8-band photometry for every object. So yes, you could guess on the probability of the mass function, right? But the point is that here, if you did, I mean, crudely speaking, this is something that's flat above the Lyman break and is a strong enough Lyman break in the sigma to noise to say, I know I'm more likely to be at redshift 2, but I'm damn well telling you I'm at redshift 10. Okay, and if you actually go to 8 sigma level photometry, which we'll come back to, the prior never wins actually. 8 sigma seems to be a sweet spot for having the Lyman break. The beauty of doing this is what you actually end up doing is you populate the MUV redshift plane with galaxies, even if some of them have been chopped into pieces. And so you can then just come along and say, I think I'd like a redshift 12 luminosity function, bang, vertically take it out of the plot. And these are the luminosity functions you get. So,
Step up your completeness.
yeah, down at the bottom end, you stop worrying about completeness, and you can see where that comes. So here, we tend not to push it. Well, you can see the error bar here. Beyond this, the completeness starts to worry. So from this study, it's the black data points and a double power law functional fit. These are some of the other data around in the literature from smaller JWST fields done slightly differently. You might ask, why is the redshift 11 luminosity function better than the redshift 10 luminosity function? Just the JWST NIRCam filters are really wide. They're actually about twice the width of wide field camera 3 filters from Hubble. And so there turn out to be some spots where it's better than others, and it's better at redshift 11 than it is at redshift 10. So you get a more sparsely function, luminosity function here. But you can see we are getting about 5 magnitudes of coverage even at redshift 12.5 here. And then, okay, we can have a debate about the form of the luminosity function. There's some evidence, although we lack enough bright data to sometimes tell if it's a Schechter function or a double power law. It seems to favour the double power law at high redshift. You then do the standard thing you then do, which is more robust than an individual luminosity function. You do a luminosity weighted integral to get the Maddow plot. So effectively, star formation rate density converted from UV luminosity density by whichever Rob Kennicott conversion you're using. Solar masses per year, if you look at the right-hand axis, per core-moving cubic megaparsec. So this is the growth of the star formation rate per unit volume. These are from these luminosity functions I just showed you. And regardless of arguments about the precise shape of the luminosity function, once you do this luminosity weighted integral, these are quite robust numbers. And prior to JWST, there was a lot of stuff in the literature saying everyone agreed at redshift 8 because that was good for Hubble, but there was lots of here Pascal's plot here, and they used to see plots going down like this, claiming that this was really the big, you know, the end of galaxies. But of course, all it was the end of wide field camera 3 at 1.6 microns. Okay. What's different now is we're not close to the end of the wavelength sampling of NIRCam yet. So this is still hopefully physical. I'll come back to this. We could only find one tentative redshift, one or two tentative redshift 14 galaxies, actually bits of two galaxies, maybe at redshift 14. And so maybe this really is finally some actual deviation, but there's been a lot of fuss because people didn't expect it to hold up as well as this. So you'll maybe have read in literature, why are there so many bright galaxies from JWST? That's kind of reflected in this plot, which only goes down about half a dex from redshift 8 to redshift 12 or 13. That's the model predictions prior to JWST. You know, so people were running models that are out by 3 orders of magnitude from the data, basically because of confusion and debates about how efficiently stars can form in dark matter halos. So why are we doing this? Well, because you might say the models were really good at redshift 8, but they pinned it to the data at redshift 8, so that's no surprise. So even actually deciding what you thought was going on at redshift 8, the actual different models deviate by an awful lot by the time you get to where we can now see the data.
What luminosity do you integrate down to for these plots?
These are down to -15, absolute magnitude.
And is the Bernoussi and Silk curve the one for like, is that their maximum efficiency one, or is that just like one of their?
I can't remember, it's from 2015.
Okay, let's.
Yeah. I mean, some of these, this plot is just to show that it's good that it's a data-led subject still, because you wouldn't want to trust the models at this point, right? Some of them are a bit cheating. I mean, Andrew Ferrara's model here in the red is really just a very simple analytical model that actually takes account of, it's 23, so he was already using some JWST data to improve it, right? So I wouldn't use this to decide who's good at simulating galaxy formation. This is just to say it's good to actually just get the data. And so there's some suggestion here that we'll come back to this, it's early days, but there's some suggestion here. We found it really hard to find redshift 14 and above galaxies. And you might say, well, I'm not surprised, that's really hard, but they're not much further away than redshift 13 galaxies, and you've plenty wave bands still. You're not run out of the edge of NIRCam, right? So, how am I doing? Probably all right. Here's a simple model we did to see if this result was expected or not. And if you go to, you'll be lucky if you don't have to do this. If you go to conferences in this area, everyone stands up and says, there's way too many galaxies at high redshift. Maybe lambda CDM's wrong, or they go through 3 or 4 things. They say, somehow star formation was incredibly efficient in the early universe. So they go, the last recourse of the desperate astronomer, maybe the IMF has changed, they say. Or maybe it's really busty star formation. Or maybe there's AGN contaminating the bright end of the luminosity function. We did something a bit simpler. We just said, let's see if it's just as you'd expect, and just make the stellar populations younger and younger and younger at high redshift, changing the mass to light ratio as you go. So what do? You make yourself a dark matter halo mass function. There's codes that you can run in this. Rather scarily, the form of the dark matter mass function depends on whose code you run by about 0.15 dex or so. But anyway, this is using a formulation from Reed 2007 and the codes that generate your halo mass function. Since we were trying to really see if you needed to change star formation efficiency, we then went to 0 redshift and looked at some of the work that's been done there. There's a nice paper, Risha Veshler, I think, is the first author on this. What is this? This is saying as a function of dark matter halo mass in the present day universe, what's the efficiency of star formation? It's basically the stellar mass of galaxies over the halo mass of galaxies. And most of you will have seen something like this, that it's most efficient about the halo mass of the Milky Way. It becomes less efficient, otherwise you'd have absolute monster galaxies instead of clusters at high masses, we think, because of AGN feedback. It becomes less efficient down to lower masses, we think, because of supernova feedback and small potential wells and little galaxies. And so you've got this halo mass function, and then the next thing to do is to bend it by what you think the efficiency is. So I should say here, people say things are more efficient at high redshift. Nobody seems to be able to agree how efficient they are at redshift 0. If you look at the different curves in this logarithmic plot. Okay, we took the geometric median of all the local determinations in the grey side. So what I will talk about now is this red curve. That's our efficiency. So you got your halo mass function. You bend it by the efficiency. That predicts your stellar mass function of the galaxies. And then because we're astronomers, we have to reverse the axis. Okay, just really annoying when you're explaining to non-astronomers. So it was mass going this way, but everyone plots the luminosity functions this way. And we turn the stellar mass function into a UV luminosity function by fitting one parameter, which is what is the UV luminosity or absolute magnitude of a fiducial 10 to the 9 solar mass galaxy. Okay, that's all we do. And if you plot that on top of the data, that green curve is the prediction of that model at redshift 11. No change in efficiency, no change in anything. Just choose your age to slide the stellar mass function onto the UV luminosity function. Now, a bit more dynamic range might change what's going on here, but it's clearly a good description of the data. It's almost too good to be true. It's so simple. We didn't even have to say maybe the brightest galaxies are a bit older than the faintest galaxies. We just assumed they're all 30 mega years old. Didn't do that. So then we thought, well, what happens if we just keep doing this? And what happens if you keep doing this? Here, if you can read the table. So here at redshift 11, we need, well, it's 29, 30 mega years, I said, it's fine. Go to redshift 12.5. The bright galaxies are holding up, so we have to make it even younger. 7, we go to 14.5, we're down to, depends on the stellar population model. For BPAS, it's 10 mega years. For Brusel-Schacht, 3 mega years. And you then say, well, I think these galaxies must have formed at what redshift, and things are really running out of time. So here's the age that we require to fit this model to the luminosity function as a function of redshift. And you're clearly just running out of time. So this model may be rubbish, but you could argue that if you thought galaxies formed at redshift 15, this is exactly what you'd predict. Because the ones at redshift 14 can't be much older than a few mega years, etc. So we've got 2 bits of evidence from this model that we're getting to an important epoch about redshift 14. First is that we need really young stellar populations, so there can't be much before that. And the second is just for looking for the galaxies, we're struggling to find things at that epoch. And these are essentially 2 independent measures. So one good thing about this Mickey Mouse model is it's got a clear prediction there should not be many galaxies beyond redshift 15. The other good thing is, without doing anything that fits reasonably, well, it's chaotic data, I admit. These are the data on the stellar mass function of galaxies from JWST at the moment, from Andrea Wiebel's work. The black points are there from Primer. So it's hard to know what's going on, but we haven't done anything to the model. We've just put it through the stellar mass function data to redshift 8. And it may be a while before we have a decent stellar mass function at redshift 10 or 11, because that's difficult. And if galaxy formation really was suddenly going really efficient, the mass functions should be different. And that's how you break the degeneracy. How do you know if you're getting bright galaxies because they're young, or bright galaxies because they're making tons of stars? Well, if you've got the mass functions and the luminosity functions, you should be able to break that connection. And at the moment, the mass functions modulo some utter nonsense out here in the green points, which is just wrong, reasonable.
In these mass functions, presumably, there is some model of the star formation that is being used to convert the photometer to stellar masses, right?
Yeah.
So that does the model also tell you that these stars are extremely young? That's a quick sanity check, right? Or is it a coincidence that you get the same?
Well, these redshifts is not too bad. It's going to be very difficult to do this test at redshift 10, 11 because you're really back into the S frame UV. With this stuff, your 444W filter at the red end is not so prone to the outshining and things. And so we're working on our own mass function paper because we're not very happy with this one. But to be fair to Andrew Wiebel, this is probably the best you could do with the first lot of primer data. But I mean, your point's a good one. We don't have any evidence about what the age of these galaxies are. We're just saying, if we don't want to change the efficiency and we don't want to change the IMF and we don't want to change anything, you can do it, but only just. And you're running out of time by redshift 14. Yeah. Yeah. Well, there is a plot we had to put into the referee that shows it's not unreasonable that I can show at the end. But the other problem is the things that we have good ages from the spectroscopy, they're not necessarily typical of what's in the luminosity function.
You could definitely get good ages for the redshift 8 galaxies, right?
From
From stellar population models of all the photometry, right? Maybe that's what I was asking.
yeah, I mean, one of the problems of this is like these are ages to fit the UV luminosity function, right? So at some level, they're never going to get much older than a couple of hundred mega years, because that's what you're using. You're using a Kennicott law that says this is star formation over the last 100 mega years is probed by rest frame 1600 angstrom UV luminosity. But you might have thought there, if that had stayed the same, if your typical age in the luminosity function was 200 mega years, well, you'd be a bit worried about that at redshift 15 when the universe is only 250 mega years old. But that's the sort of assumption that people made to say the thing will just fall away. I mean, another way to say this is here, if you look at the halo mass function, it's falling away like an absolute train at this epoch. And what we've done is, it's like the tide going out, but we're somehow keeping the boat up above the water by making them younger and younger. But then that means when you can't make them any younger, they're going to be gone because there's hardly any halos to put the galaxies in. So the prediction is a sudden drop-off, which is not often seen in astronomy, I agree. And if you worry too much about the detailed mass functions, but you do the mass integration of the mass functions to get the stellar mass density as a function of redshift, these are the latest data from some of the recent publications. The Shuntov stuff is crazy at the high mass end, but actually that's not what dominates the mass density. And so again, we've done nothing to our model to change efficiency or anything, just goes through everything. We did start a bit late, right?
You started late,
yeah. I'll finish. So some of the predictions, right? This is the reason we probably shouldn't record the thing, but anyway, who cares? So there's a prediction here, there'll be nothing really very much beyond redshift 14. Well, not nothing, the universe is never quite like that, but it's going to be a drop-off in galaxies. And therefore, you may have seen 3 papers recently. There's this paper that came out of GLIMPS, which is a very deep survey claiming to have lots of galaxies at 16 to 18. The paper was submitted, this is all photometric redshifts, by the way, none of this is spectroscopic. So they'd found 5 galaxies out here, the JWST. But if you apply this luminosity function prior that I described, all of the redshift 16 galaxies we would say are down at redshifts 4 to 5. Essentially, it's the Balmer break instead of the Lyman break. I can't say any more of this because they refuse to do this luminosity function prior. But the fact that when we do this, because the good thing about this is it's all public data, so we just reduce it ourselves and do the same analysis. We don't see any of these objects standing up. They had 5 galaxy candidates. I know there's nobody in UCLA on this paper, so this is fine. If you're mad enough in the archive to look at the final accepted version, it's got 2 galaxy candidates. Neither of these 2 galaxies were in the first paper. So 2 different galaxy candidates to the 5 original candidates. I don't believe any of these objects are at redshift of 15. More nonsense, and this is real nonsense, as described in the title of the paper. It should at least be rise of the extragalactic empire. Right? This is not galactic astronomy. And this is really mental. So this is redshift 17, redshift 25, and they go on to do the redshift 25 luminosity function. There was a redshift 40 luminosity function came out on April's Fool's Day, but this didn't. There's a really grim April Fool's Day in the archive if anyone was at it. There was about 10 April Fool papers. And this would have been fine if it came out that day. So we reduced our own version of this data self, and here are 2 of the redshift Z20. These are 2 of the redshift 25 galaxies that go into luminosity function. We couldn't find the other ones, but there it is. It's actually at its best in the 115W filter, right? 1 micron detection. This one's certainly there in the 2 micron filter. This is with the referees, whoever they are. If this paper gets published, then we might as well all give up, honestly. And
Sorry. Editor of everything.
yeah, I've spoken to the editor. I've spoken to the editor actually.
Secret council of astronomical journal editors.
Yeah.
Don't let this get accepted anywhere else when you resubmit it to it.
Well, this was a problem, right? Papers disappear and then they reappear. This is not even at the subtlety of piles, right? This is just the chi-squared versus redshift for these 2 objects. You know, high redshift solutions are actually excluded by the data for these objects.
And how do they defend it?
Sorry?
How do the authors defend this when you show them?
Well, I've shown them in conferences, and bizarrely in conferences nowadays, it doesn't matter what you say because they're mainly looking at the laptops and they get up and they give the same talk. Anyway, it's fine. Sorry, Ned, you were going to say something. Or maybe not. Did you want to say something, Ned?
Yeah, I have a general comment about your luminosity function priors.
Maybe we should save it to the.
Yeah.
Let's do that after.
My point is that that's not needed here. Okay. Tommaso and I have discussed this because he's on this paper. It's actually not quite as much nonsense. Okay, I mean, it's the same thing, right? I mean, you get solutions at redshift 17, and there are alternative solutions. To be fair to the authors in this paper, they expose much more clearly that the alternative solutions exist. But again, in an object like this, you can see the galaxy here in the 200 filter, and you can see it in the 150 filter. Some of these are going on to a mask at the moment, and so they're being checked out. Derek McLeod, who's my postdoc, I don't know how many people know Derek, he's a lovely guy. He's insane, so he's reduced all the NORCAM data that exists using the pencil program that Dan McGee wrote for us for Primer. It's 130 fields, it's about half a square degree. Cosmic variance isn't really an issue. He stayed at 8 sigma. He's got 1 redshift 15 candidate, and JWST have thankfully given us NIRSpec time in cycle 4 to check it out. So we can't find them. Everyone else can find millions of them, but we can't find them. Oh yeah, that's just, this is what happens. Sorry. This is, so I've got Derek's permission to show this. This is what happens to you if you do that. Okay. Well, yeah. Okay, some quick other predictions. Because we just do a modified version of the halo mass function, which actually flattens, this is the faint end of the luminosity function. We predict that the faint end of the luminosity function does not get steeper and steeper and steeper. You might say, who cares about that? But it's got a lot of impact on the UV luminosity density and how many photons you get for reionization. Here's the prediction of our model. Here's the old-fashioned extrapolation from Richard Bowen's work. I'm not criticizing that. It was kind of right at about redshift 7.5. This is a bit scary though, because these are recent attempts at JWST to measure the faint end of the UV luminosity function. This is going to be hard work. It's going to require massive integrations to do this work. But that's another clear prediction. In fact, it suggests that it should get shallower down low. Well, I said in the mass function, these points in these mass functions are just wrong. They're the wrong redshift. If they should be at redshift 3 and you put them at redshift 8, you end up with a really high mass, and you can see that's going on here. The rest of this mass function is all right. If we put our model through reionization and give everything an escape fraction of 20% and solve the differential equation for reionization, the prediction of the model is the black line. These are the data at the moment, the latest data, including Planck's middle number for a step-like reionization, and some nice grey shading from Charlotte Mason, the range of models that she's got. So it starts about redshift 12 and it finishes around redshift 6 or 5.5. This bit here requires a more sophisticated calculation that we don't do once some of the mean free paths get very long. And yeah, I won't labour this point. One of the neat things about this model is it makes a prediction for the sub-millimeter galaxies, so it connects again to ALMA. So at redshift 11 or redshift 12.5, this is the model with no dust, and the green models with the dust, and it doesn't make any difference because we don't have many massive galaxies, and there's not much dust meant to be here. By the time you get back to, say, redshift 9 here, so I don't know what's happened at the bottom.
We'll do in the questions.
Okay, I don't understand that question, but that's fine. In our model, there are these galaxies, these higher mass galaxies that have got to be taken out by dust to fit onto the UV luminosity function. So you can actually predict how many sub-millimeter galaxies there should be because you've got to hide these galaxies. And in this model, if it predicts about 1 or 2 redshift above 6 sub-millimeter galaxies per square degree. And if you're one of these people who wants to increase the efficiency a lot, you way over predict the sub-millimeter galaxy number count at high redshift if you do that. Okay, there are my main conclusions. Slow evolution of the UV luminosity function, just an observational result, and hence star formation rate density from redshift 8 to 13. We agree there's a surprising number of bright galaxies. We struggle beyond redshift 14. We use this simple model to say you can do it. Doesn't require anything to change, but you have to make things very young. The one that people like about extra efficiency, it tends to overpredict the mass functions and the sub-millimeter number counts. If you believe the model, then the drop-off at redshift 15 is likely to be real because we don't see many stellar populations at redshift 14 that are very old. And we are now involved in Primer doing what it was meant to do. There's 2 major spectroscopic programs, Cycle 2 XLs that Alice and other people here are involved in as well. And CAPER's now underway, led by Mark Dickinson. You can see where all the NURSPEC pointings are in the Primer fields. And this is from last week. 2 nice CAPER spectra at redshift 9.1. The things we selected to be at redshift 9. A beautiful little red dot. It's a different talk, but here's a very red object that turns out to be at redshift 9. Oh, and there's that's one of these objects I talked about in Marco Castellano's paper. We've got a spectrum it 2 days ago. It's at redshift 3.65. That's H alpha and oxygen 3. So eventually, these objects within reason will be checked out by the spectroscopy. I'll leave it there. Thanks.
Thanks, Jim. That was fabulous. Okay, so maybe we can get to Ned's question. Then we had a question also in the chat.
Yeah, so the luminosity function prior. I mean, certainly there's more faint galaxies, less luminous galaxies, but large ones, high luminosity galaxies. But when you're trying to work at redshift 15 or 16, you don't have prior information. And so the prior is uncertain or based on prejudice, not data.
No, I think you're overrating the sophistication of the prior, right? So we know the luminosity function at redshift 8 is already well down from redshift 2, 3. A simple extrapolation, the power of the prior is not at all critically dependent on whether it's down another dex or half dex from redshift 8. It's not this closed loop. It just basically says, I'm sending you to redshift 2, 3 unless you tell me your data is good enough to keep you at redshift 15. And we've tried this, we've tried lots of it. You don't get any different results changing what people think is going on, because we're not even now, people are now agreeing by about redshift 9. Well, everyone agreed by redshift 8 because Hubble was quite good there. So the prior would be fine, even if you just adopted the redshift 8 luminosity function and said it was the same at redshift 15, the power's about the same.
Okay, we have a question from Matt Walken. Okay, so does the prior take into account the strong selection effect that all these surveys are strongly biased towards finding galaxies that just happen to be in the middle of unusually strong star formation bursts?
Now, again, you're overrating the sophistication of the prior. This is just about the number density of galaxies if you don't have good information on their SEDs, where it would be if you basically had hardly looked at it. And people say, oh, these are unusual galaxies because they're fairly blue and they've got a break. But actually at redshift 2, your average galaxy is fairly blue and it's got a break. So you're not looking for weird, extremely red things. You're looking for things that are fairly flat in F nu. That's the typical high redshift galaxy, and then has a break. And the question is the break strong enough to rule out two alternative solutions? Either it's a Balmer break, or sometimes with these big broad filters, it's just a dusty galaxy that gradually gets down and disappears in the shorter wavelength filter.
Like the redshift 716 candidate who turned out to be a redshift 5.
Yeah, well, yeah, it wasn't.
So that's another case, right?
That's a pathological, yeah. So some of them have turned out to be. We now know that at very high redshift, you get O3 equivalent widths of like 2,000 or 3,000 booming H alphas. And there is the odd pathological case. We had an object that we and everyone else thought was at redshift 15. But H alpha happened to be, it's at redshift 4.9 exactly, we now know. And at that point, H alpha straddles two broadband filters and goes into the medium band 410 filter in a way that, well, I can show you that if you want. It's a bit of a technical point. It's my last slide in the spare slides. So this is how scary it can get, right? So here's the photometry for this object. Bang, 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 nice flat F nu UV continuum. Big drop, okay, it's in F2000, but if the break's there, it's past in F2000. The actual spectrum is here. Booming, whatever it is, 37, 27, would that be? I can't remember now. Anyway, booming lines with this one in particular, H alpha, I think it'll be here, or yeah.
That was 5007.
Yeah. Yes, and then H alpha here happening to be exactly at, basically, it falls into the 356W filter, the 444W filter, and you can see it has actually raised very slightly with 410M. And yeah, this is what this one's chi-squared solution looks like. This is really pathological and weird. It's either a redshift 16.5 galaxy, or it's exactly 4.9. In fact, it's the greatest photometric redshift ever predicted once you put in a model with enough strong emission lines. That's a freak case. There's a few of these, although that did result in the community. I mean, you look at it here, you think this, if all you've got is this photometry here, that taught the community to include new sets of templates with really extreme emission lines in them that can completely contaminate even these broad filters.
Sure. So I have a question about the model that you had with efficiency, and you, as you explained, I see, right, we understand that the small masses come from supernovae, maybe, and the high masses come from maybe AGN activities. But then you kept that type of a shape and you applied it everywhere. So if you take this model at face value, does that predict something about, let's say, the black hole seeds that grow, and then, you know, the efficiency of supernova feedback that's very early in the growth? I mean, this shape, if it is coming from where we think it is, it has huge ties to how galaxies evolve in together with the black holes and the stars.
Yes, I mean, it's a very fair question, but whether we actually know enough about the efficiency, my point here was, this is the disagreement about the efficiency at redshift 0. So you're baselining.
The disagreement that maybe in supernova is larger, but the disagreement is right in the EGN is not that big. I mean, within all the uncertainties that we have. So if you take that at face value, that says huge things about black holes. You can actually try to estimate what are the black holes. These are black hole, intermediate mass black holes and smaller black holes have the same feedback.
You'd think, and so we thought this. I don't intend to do this today, but if you look in the follow-up 2005-25 paper, which was accepted a couple of weeks ago, we did put in another model where we just made this flat at high masses, right? Just as an experiment to see, because you might think, well, there's going to be supernova feedback in the young universe, but maybe there's not enough black holes to do the mass feedback. So we flattened it, and with the data, it makes no difference to the UV because we're not at high enough masses, right? But it does actually predict too many submillimeter galaxies because you start forming these big massive things that are not in the UV. So not good. You can play with this quite a lot, and it does, this actually has more effect when you're comparing to the JWST data and what's going on. But my point is that, you know, people just say things like, we know it's much more efficient at high redshift. No, you don't. In fact, you don't even know what the efficiency is at redshift 0. And if you just take that red curve and slap it through everything, it's not true we don't do anything. We have to go for this very young age to change but that's it. And if that's wrong, then you would have to put in efficiency. So that's one first and then Ned. So at the back.
I want to get Eric
Yeah.
in the back.
Yeah.
Also in the front, but-
Yeah.
So let's get Eric in the.
But just, you know, you had a prediction about the number density of galaxies and see if it's, you know, what sort of observational campaign do you need to confirm the prediction? Or something super deep or why?
Well, this is debated a lot, yeah.
Well, I would say no. This was my point about Derek's insanity. Because the point is the galaxies we know at 13.5 are not that faint. It's the bright end that's holding up. So it'll be very hard to say something about faint galaxies, but you can ask the question, given the bright end of the luminosity function of redshift 13, you should be able to see redshift 15 galaxies if they're similar bright things. And at least searching across all the data, can't see any.
I think, okay, you didn't talk about this part of the Castellano paper, but the paper that Tommaso's on about the candidates, they actually talked about different observational campaigns that you might be able to do to place constraints on either the bright or the faint end. And in non-lensing fields, it seems like thousands of hours are required to do the photometry, right?
Point here is that research you guys did was limited to 8 sigma, so it's really the very brightest, right? And then you expect 1 and then 0 and 5.
Well, it's not the brightest because 8 sigma in the Midas field or NGD jades is quite faint, actually. Yeah, okay.
Right, and you need a lot of hours to do that. I think that's true because even if you find one, what does that teach you?
Yeah. I mean, the answer is a really wide, really deep NIRCam survey with, you know, at some point JWST will hopefully do 1,000-hour type candles thing, right? That's how it needs to be done.
But then there's also discussion of how much you want to use medium bands versus broad bands, you to exclude, to basically constrain the presence of emission lines and how.
Yeah,
do you think
but I mean-
that is?
Yes,
Just show.
but there's some redshift regimes where the broadbands are fine, like just where the break aligns nicely with the broadband. So a bit like we have with Prime, you'd probably start with the broadbands and then supplement it. But if you're just trying to ask the question, is there anything above redshift 15? A very deep broadband image would be what you'd do.
Ranga and then Sean and then Nick, because you already asked a question.
So, given your derived median ages that you quoted there at each of those redshifts, it's very hard to reproduce the emission line equivalent weights of several hundred to several thousand angstroms that we're getting for these high redshift galaxies.
Those are the,
So-
that's extreme.
Huh?
That's
No,
the
but-
extreme.
But
that's
typical
typical.
is 300. The median at redshift 6 is 300 is for the ones we can measure. So Do you want to comment on that? I mean, unless you put in a contrived star formation history, fine, you reproduce the UV luminosity function and the mass function, but how about the equivalent width distribution of the UV slopes?
Oh, the UV slopes are fine because these things are dust free at redshift 11. They're not high enough mass. None of them are high enough mass, even according to the present day dust mass relation. So Ferrara's got a model that has no dust in it, and it also works fine.
No, I'm not talking about, I'm talking about age dependent UV slope, not dust.
Well, but what I'm saying is above redshift 11, things do move pretty quickly to a UV slope of minus 2.5, as you'd expect from a very young population. I mean, there's all sorts of technicalities about whether it gets dominated by 2-photon continuum and doesn't become as blue as a young stellar population. But booming emission lines is good for a young population.
No,
So
you can't, but 100 million years is too old to get those.
Well, Yeah, I think I would agree.
well, I'm not bothered about that. I thought you were bothered about the 5 mega year at redshift 13.5.
The ages, the young ages people have found at redshift 8 compared to your 150 million year age at redshift 8. I think
But we don't know what the equivalent width line distribution is for things that dominate the faint end of that UV luminosity function. In fact, there's arguments that they've gone into an off phase and won't have very strong lines, and when they have a burst, they get bright lines and they go motoring up to the bright end of the UV luminosity function, then retreat again. That's what Ryan Ainsley would say from his work.
let's have Sean ask the last question and then we should have other questions offline.
If the primary contaminant for like the lower redshift emission lines, could you not supplement a like wider filter sort of campaign with medium filters that are looking specifically for this line or this?
Yeah, I think, so I showed you a pathological case. Most of the things that Meyer just takes you to, it's more a Balmer break than a Lyman break. So, but you're right. And in cycle 4, we and 3 other groups applied to add all the medium bands to primer. We had a shit cycle 4, but so did many other people. Anyway, Adam Muzan's group got the medium bands. It's all going to be public by the end of cycle 4. There'll be medium bands for all of them. No, it's not all of them, but you basically you want to cut the F200W filter in half, and you want to. So there's a sensible choice of filters that you can do this with that get you maximum. And independently, most of the groups chose the same. This has already happened in Jades and Good South, and it's a sensible choice. You basically, if you can. You don't need all of them, but if you get a medium, you can then subtract that from the 200 to get the other half, etc., etc. And so with a judicious choice of medium band filters, you can sort it out.
Okay, so let's thank Jim for the great talk and tour de force.